G'day, in this video we are looking at the photoelectric effect and how it fits with the quantum model of light. So we're looking at dot point 7.3.2 and 3. We're looking for evidence that's supporting this idea that light behaves as a particle and the implications for this evidence for our understanding of light being quantized and fitting inside what we now know as a quantum model. So we're going to be looking at evidence from the photoelectric effect that demonstrated how light was not behaving like a wave. And we're going to be analyzing the photoelectric effect in this formula here, K max equals HF minus phi, for what we observe for metallic elements which are experiencing this photoelectric effect. Effectively, this formula allows us to maintain the law of conservation of energy for this phenomena. So to be able to get there, we have to talk about what the photoelectric effect actually is and how it works, and then be able to quantitatively account for some of the energy changes that occur when electrons are ejected from a metal when the photoelectric effect occurs. And then we're going to be talking about the implications for how this fits with the quantum model of light. So there were some early experiments done where people were observing this photoelectric effect. Photo meaning light, electric meaning the production of electricity. And this could be achieved when you had electromagnetic radiation striking a metal, sort of in this diagram here as it's shown. Essentially, when that light strikes the plate, it's going to generate a current. Now, not a current through a wire, so to speak, but the moving of electrons from, in this diagram, point C to point A. Essentially, they were called at this stage cathode rays. We now know that these cathode rays are a stream or a beam of electrons attracted to, in this case, the positive terminal on the other side of the apparatus. What they also learnt was that there was a critical frequency. Under certain frequencies, they weren't able to produce their cathode rays. They couldn't produce electrons. And if they got above the critical frequency, the electrons were produced and there was a stream of electrons, a cathode ray created. Something else to note is that this critical frequency is different depending on the metal that you actually have. They have different what we call thresholds. There are also the number of electrons that are being produced, which we can measure with the current that's flowing through. Essentially, they were not dependent on the frequency of the light, but rather the intensity of the light. And according to the wave model, they expected it to go the other way around. They thought high frequency, high energy, more wave fronts contacting the plate itself. More wave fronts mean more electrons mean more current, was kind of the argument that they were going for. But rather what they saw was that intensity of light, in other words, more light striking the actual plate, led to more electrons being produced. So to explain some of the phenomena here, we can start to use energy concepts to get there, particularly around how and why we have a critical frequency. Essentially, low frequency light has low energy. And when we are putting light onto the metal plate that's here and it's striking electrons, there needs to be enough energy supplied by the light to the electron to dislodge it from the metal itself. In the same way that we need a potential difference to generate a current to move electrons off an atom, we need to achieve the same thing when we have light being emitted and striking an electron on the plate. There must be enough energy to dislodge it from the positive nucleus of the atom. And then after that, if it's able to absorb excess energy from the light, then this will result in the electron having kinetic energy. Essentially, it's the difference between the threshold energy to dislodge it. The remaining leftovers will just all be transferred into kinetic energy for the electron. We can actually measure this kinetic energy in an apparatus like this by using what we call a voltage divider. Essentially, it means that we can change and control the potential difference between X and Y. If we change the potential difference in such a way, like is being shown here, where they've essentially just flipped the battery, you're going to be able to pull the electrons back in the other direction. Or if it's not enough to just pull them back straight away, we're at least going to be doing work on the particles to provide a resisting force. Essentially, we're reducing the kinetic energy to a point where eventually the electrons won't be able to across the boundary and end up producing a current. So in other words, we just keep increasing the voltage over and over and over again until we're not getting any more current through our circuit. If we're not measuring current, then it means that no electrons that are being dislodged and going to the other side. What that means is if there's no more current, then electrons that are being dislodged are no longer making it to the other side. If you've hit that kind of threshold voltage where the current finally stops, we call it the stopping voltage. It's that break point where there's now too much voltage to get the electrons across. We know that at that stopping voltage, for the charge of those particular electrons, a certain amount of work is being done to stop those electrons from moving any further. If that's the case, then we can assume that the work that's being done on the electron is the same as the initial kinetic energy of the electron, because essentially all of that energy is now being consumed and it can't get to the end anymore. What these concepts sort of all come together and result in are graphs like these, and concepts of maximum kinetic energy, the energy generated by the light itself, and what we call the work function. Now, the work function, what it describes is the amount of energy required to dislodge the electron from the particular material. In other words, if we put energy into the electron and take away the work function, the amount of energy just to get the electron off the metal itself, then the remaining energy is Kmax, so maximum kinetic energy that the electron can have. And again, we can measure that by putting an opposing voltage on and figuring out the work required to stop the electron from getting from one plate to the other. It's quite common to look at graphs like the one below, and essentially what you can do for a particular substance, let's say that we're looking at the magnesium one, is plot different frequencies of light against the maximum kinetic energy that that frequency of light can impart onto an electron. And we should get a nice line of best fit. If we extend that line down here, wherever we've got our y-intercept, what this is indicating here is the work function for that particular metal. In this case, the work function for magnesium is approximately 6 times 10 to the negative 19 joules, which is quite fitting because this here is our y equals mx plus b formula for this particular graph, where Kmax is the y value on any point of the line, f is the x value at any point of the line, h is meant to be m, so in other words, Planck constant is the gradient for each of these lines, and that's consistent because they all share the same gradient. And phi here is the work function, which is akin to the y-intercept. So the only difference between each of these materials in the graphs is not the Planck constant, but you will end up getting different k and f values simply because the line starts at a different y-intercept. So early scientists that were working on the photoelectric effect, using their concepts around the wave model of light, came up with the hypothesis that if they were to increase the frequency of light, this would increase photocurrent, just like we talked about before. This idea of more wavefronts means more interactions with the electrons, therefore more electrons are produced and we have a greater current. However, this did not match up with measured results. Essentially, what we saw instead was that the number of electrons produced did not depend on the frequency of light, but instead, if the intensity of light was increased for the same frequency, we saw a greater photocurrent. In comes Albert Einstein, bringing together things that we learned about the other day with Wien and Planck, and now what was observed with the photoelectric effect, to now talk about how all of this explained the idea that light must be quantized. In other words, that light comes in packets, and that in this case, each packet that was incoming to the metal was able to interact with one particular electron, give it the energy that it needed to escape the work function, and then any excess energy from that packet, from that photon, would just result in the electron having kinetic energy. In other words, if you then had low intensity light, then you would have less photons than you would with high intensity light of the same frequency, and thus this then begins to explain why we get a larger photocurrent with high intensity light, because there are more packets of energy, more photons to interact with more electrons, and dislodge them and get them to generate their photocurrent. However, there is quite an easy misconception to make because intensity is not just a measurement of the number of photons of light or the rate of photons that might strike a surface every second. It's a little bit more complex than that. So notice before that I was talking about the idea of higher intensity light having more photons for light of the same frequency as compared to this low intensity light here. And that is because frequency also has an influence on light intensity as well. So there can be some scenarios where we're looking at the photoelectric effect and we're looking at different types of monochromatic light of different frequencies, and the assumption that intensity just automatically means more photons becomes not entirely true anymore. So I want to break that down so that we don't incur that misconception a little bit later. Essentially, increased intensity does not necessarily always lead to an increased number of photons and therefore an increased photocurrent. It will if the frequencies of the two different light sources that you're comparing are the same, because intensity is also dependent on the frequency of the photons. So to break that down, we're going to look at our formula for intensity. And essentially, intensity is a measure of power output from the light divided by the area that the light is striking. And there are a few different elements to this formula so that I can expand it out a little bit more that we're going to want to keep in mind. First off, that power is essentially energy output over a period of time, and that the total energy of our photons is equal to what we would call NHF, where N is a little bit of an add-on to the Planck formula that we've already looked at before, where N essentially is the number of photons. So we can use E equals HF as per normal to calculate the energy of a single photon, but if we have 2 photons, then we need to double that energy. If we have 10 photons, then we need to multiply that energy by 10, and that will give us the total energy of all of the photons collectively. So what this means is essentially that the intensity of light is equal to the energy of all of the photons that's striking a particular area divided by the time it takes for all of that energy to transfer multiplied by that area. So all I've really done here is replaced the power at the top of the formula for E divided by T. However, I'm going to take this a step further again, because we know that the total energy of all of the photons is equal to NHF, the number of photons multiplied by the energy of a single photon. And that's still going to be divided by T multiplied by A. Now what I'm going to do is I'm going to separate out the formula into some chunks. I'm going to say that the intensity of light is equal to N on T multiplied by HF multiplied by A. And there's a reason why I'm doing this, because essentially this N on T value we could say is the photon rate. How many photons are striking the surface every second? We've also got HF, which is the energy of one photon. We've also got A, which in this scenario we're going to assume is a constant. That's going to make this last little bit a bit easier to work with. So if A is constant, we can say that the intensity of light is proportional to the photon rate and the photon energy. Therefore, the conclusion that we can make is that if I and A are both constant for a bunch of different scenarios, if I were to increase the frequency of my monochromatic light, then that is going to cause an increase in energy, HF, right? And that is going to mean that in order for the intensity of light to stay the same, there must be a decrease in N, or photon rate. And similarly, if I were to get the photoelectric effect to start happening, but I was doing it with a lower frequency light, then that's going to decrease the amount of energy, HF, which, if the intensity is still the same, would mean that there is an increase in the number of photons to maintain that intensity. Because again, intensity is not just number of photons, it is dependent on the number of photons and the energy of the photons as well. If we're still a little bit stuck on that one, I'll build on that a little bit more with you in class and try to break it down. It's rare when a question would come up that would require this knowledge, but it's not unheard of, and it's worth kind of getting your head around, because if you can get this, you can it kind of proves that you understand a lot of the other basic principles around the photoelectric effect. So it's a bit of a short one. This brings us to the end of inquiry question 3. The next 4 videos all look at inquiry question 4 as we start to unpack a lot of Einstein's work, particularly around special relativity. He came up with some postulates which are really important in understanding the rest of his work around special relativity, and he talks a lot about frames of reference. So the first video is going to be unpacking a lot of those basics so that we can start to explore Einstein's work and ideas confidently and comfortably. But until then, have a good one.